Hi, I'm Sebastian, and I would like to talk about a project of mine that I've been very enthusiastic about, which is long-range fiber optic earthquake sensing. And really, the... Do you have to press OK? Yeah. There we go. Oh, OK. This is difficult to handle. OK. Can we just leave it up? It's fine. OK. Yeah, so what I do like about seismology is that most of the stuff we're doing is data-driven. Like we do have quite a lot of data, and but the problem is this data is mostly, of course, biased, and you can have blank spots. So for example, here, this is from an application for global seismology, where I collected some data. And mostly, if you're working on a global scale, the data coverage will look kind of similar, that you have a lot of stations in some areas, here, for example, North America and Europe, and then barely any coverage anywhere else. And our most prevalent blind spots, really, are the oceans. So, and that's something that people have been thinking about for quite some time now. And one avenue to potentially get data in the oceans is with the existing telecommunication cables that are in the oceans from all of these internet providers. And we are heavily connected. And we are all aware that there are options to get data from fiber optic cables. And you potentially think, well, just use DAS. You know, everyone is familiar with DAS. I don't want to spend too much time in explaining how it works exactly. But essentially, if you have a fiber here, and you plug in a laser signal, you get some backscatterers from along the cable, and if there's some deformation, you get a phase shift. And these backscatterers here, they lead to a really nice, densely sampled line, so you have a lot of channels. And here, for example, that's a very, very nice earthquake measurement from a cable. You can see that you have measurements on several channels. DAS has been used quite a lot, also with a lot of success, dare I say. And it is quite nice because you have the dense channel spacing. You can have versatile usage. You can even use it in this very valley on some mountain slope. I'm looking at you, Jared. And you can use it on existing infrastructure. So if there's a dark fiber, you can just plug in an interrogator and start measuring. It's all very nice. But there are also some problems if you want to monitor the oceans, because DAS only has limited range. Because you're reliant on measuring the amplitude of the backscattered laser signal, and these amplitudes do get quite small the longer you measure, and it's a bit uncertain how far this range actually is, but it's somewhere between 50 and 100 kilometers. It's not going to be enough to cover an entire ocean. So if you want to get data from the oceans for long distances, DAS ain't it. It's not going to work. And besides, interrogation units can also be quite expensive. So there are some downsides. How you can potentially solve this is that you're not, well, reliant on these backscatterers, but instead measure the forward laser signal here. This the transmissed laser signal that will have much higher amplitude, and measure the phase shift on this one. With this, you can reach much longer distances. And essentially, what you're going to be sensitive to, you can show it's going to be this phase shift is going to be proportional to the integrated strain along the fiber. For example, now, for this measurement, it may look something like this here. So you integrate along the cable, and you still get an earthquake measurement. Of course, if you have the DAS measurement, you never would use the integrated strain. You lose quite a lot of data. But here we're now interested in situations where you don't have this measurement, and this is all you got. So my project in this is kind of to understand how can we use this data. But first, I also would like to talk a bit more. So you lose the dense channel spacing, and instead only have a single channel. So it's going to be more difficult to interpret. There have been some methods proposed over the past years how to get these measurements. There's been some great work by Giuseppe Mara's group. There's been some other methods. And honestly, from a seismological point of view, it does not really matter how you make the measurement. Like, in the end, you're going to measure the same thing. But still, I would like a bit to talk about what we've done in this project, which is using active phase noise cancellation, where we work together with the Swiss Meteorological Institute, where they managed to get a measurement for this. So what they've done as a meteorological institute is that they distribute very precise time steps throughout the country. They have their main base in the city of Bern, and they have a cable where they send time information to Basel. This cable is 123 kilometers long, and because it needs to be ultra precise, the cable needs to be stabilized, but they cannot control this. The cable is just plugged there by some telecommunication company. So this cable will be subject to noise. This noise might come from temperature variations, so the noise will kind of vary within the day, or also mechanical deformations. And these mechanical deformations is exactly what we're aimed at. So they are sending in the time information from Bern to Basel. It's subject to noise. And they are having a very smart method how to determine this noise by sending in a monochromatic laser signal. And with this phase shift that they measure on this monochromatic laser signal, they can estimate the noise and directly remove it from their own measurements. And then for the meteorological applications, they basically have a noise-free measurement. And this noise from the meteorological application is our data. So, and because I personally don't really know a whole lot about lasers and how this works exactly, I like to imagine that our data is really coming from noise-canceling headphones that they plugged onto this fiber optic cable. Yeah, this was all nice theory until we actually measured an earthquake. In September 2022, we received this raw data and also filtered data from the Meteorological Institute, where you can see a crystal clear earthquake signal. This was an earthquake in Alsace, close to Basel, of magnitude 3.9. And now my job in this project was really, can we simulate this? Can we reproduce this with numerical simulations somehow? So for this, we can set up some numerical modeling. We use the software Salvus for this, for full waveform simulations. And really what's going to be important is the line geometry here. And you can see that the line can vary, especially within the cities, on really small, spatial scales, just on the order of tens of meters. And we can also include topography and all of this into the simulations. We can take the information from existing earthquake catalogs, and you can see over the line the nice waveform move outs. And what we're going to do then is going to extract the strain along the line and integrate over it and try to compare it to the observations. And you're going to see the difficulty is that the line sees the same wave field at different points all the time. So it's going to be quite complex to interpret, but first to show that this what we've done is actually kind of realistic. Here it's the same measurements at the traditional seismic stations. This is for the same simulation. And once if you integrate the strains along the line, you get this result here, where in red you have the synthetics and in black you have the observations for admittingly pretty long periods. This here is now for periods between 6 and 17 seconds. But you can see that the waveforms are actually kind of fit. Like the shape overall seems to correspond to each other. There are some problems in the time arrival. So for example, here it arrives a bit too late. Here it seems to be a bit too early. There's a lot of complications. But overall, the shape is replicated. And this is great results, really. At least we think so. So this unlocks the question, can we do somehow quantitative seismology with this? can we not only replicate the observations, but can we actually learn something new about the source? Or can we even do tomography with this? And for this, we set up a simple moment tensor inversion, just a linear inversion scheme where you can compute Green's functions on this single channel. And here, for comparison, is from different earthquake catalogs, the moment tensor solutions that you can look at. And if you now only use the single phase noise cancellation signal and do the linear inversion, you get this result, which pretty much falls into the realm of possibilities, and you get a very similar source mechanics. And I mean, this is amazing. So you can only do this with a single measurement. You get the full moment tensor solution. So the information in this kind of measurement seems to be incredibly dense. Now I would like to talk a bit about why this is possible. And for this, I would like to backtrack a bit and talk about the sensitivity of these lines. So because we're integrating over the entire thing, and let's say this is a fiber again, we have some earthquake, and we have an elastic wave traveling over the fiber. If you now just imagine for a second that here the fiber is fixed, and only here you have deformations, and you will integrate over this straight cable, you're not going to see a thing. You're essentially blind to it, because the deformations are exactly compensated where you have the same amount of compression of the cable and stretching, and if you integrate it, it's going to be 0. You're blind to it. So let's just move the wave along. But if you paid attention, there are 2 spots where it's not compensated, and it's going to be exactly at the start and the end of the cable. So this may be bad news. If you have a perfectly straight line, you will only be sensitive at the start and at the end of the cable. Now let's change the line geometry a bit, do the same thing again. And now you can see that at this point of curvature, you also have a bit of sensitivity, because you can actually stretch the line in this way without compensation. So what we've learned from this is that the sensitivity is really in the curved line segments and start and end of the cable. Now, if you're going to take this analytical example of a measurement and some earthquake where you have a line here, you can still do normal, like seismic phase picking, for example. But now you're not going to have just a single P wave arrival. So here, for example, you would have the P wave at the curved segment closest to the source, but you will have multiple P wave arrivals at all of the curved segments. You will have a lot of these, and you can do the same thing for S waves, where the S wave will arrive at the curved line segments. And of course, this here is a very simplistic example where you have this kind of geometry, and all of the arrivals are kind of after each other. But this is all important to understand why the moment tensor inversion works, because there's a lot of information in the direction of the flip. Overall, you can, in fact, learn about a lot if you know the geometry of your line. And you can even go further and say, well, you can do tomography with this. If you just have one measurement here, and you just look at this window, for example, you're going to be sensitive to a specific volume of your subsurface. If you then look at a different point in time, you're going to be sensitive to a different volume of your subsurface. And this you can really do with all kind of windows in your measurements. These are all analytical examples. Here's some more rigorous numerical examples where I computed for this event that I showed before some VS sensitivity kernels for different line geometries. Maybe it's a bit difficult to see, but here the line geometry is really simple, and here it gets more complex, and this is the full line geometry. And you can see that the sensitivity changes drastically. So from this we learn that the line geometry needs to be known, to a high degree, and you really need to account for all of these little bends, because it does change the curvature and therefore the sensitivity by quite a lot. Yes, and as a last thing I would like to talk about is towards going towards tomography with these types of cables. And for this, I just set up a very easy toy example. I don't think a data set where you can actually do this exists at the moment. But this is a very simple toy example where you just have a line, you have some curved segment, and you also have a straight bit here. I just randomly scattered 15 events in this area, and these observations kind of look like these lines here. And then starting from a 1D model, I just started to iterate and did a full waveform inversion. And this is the result. This is the ground truth. I just plugged in a checkerboard. And you can see that you actually can recover the checkerboard to some extent. So these points here, they overlap with the red points over here, and you also have the blue dots overlapping. So this is really just a kind of proof of concept that this data, even though it seems so complicated, you can learn something about the subsurface. You can do tomography if you think about it the right way. It's also just to show that you have some sensitivity in depth. This is now at a point a bit deeper, where the checkerboard is actually flipped. If I go back and forth, you may be able to see it. And also in the inverted model, the checkerboard is indeed flipped. So you do have sensitivity in depth as well. So yeah, here I'm at the end of my presentation. I just would like to tell you some take-home messages. So really, this entire method of having this phase transmission data is in its infancy, and it's really still at the start, and we are still trying to explore what you can actually do with this data. But it does enable the long range, potentially thousands of kilometers, sensing of these cables, so you can, in theory, interrogate the transoceanic cables. The phase noise cancellation that I presented is maybe one method to do it. At least if you collaborate with a metrological service, it's really at no additional cost or effort. At least according to Dominic, he just had to plug in a hard drive and started collecting, because usually they would just throw away this data. And it can work without interrupting the metrological service themselves. So yeah, I really think this is an interesting kind of data. It's of course very challenging, but I think there are a lot of promises as well, because we showed that the moment tensor inversion with a single time series seems to be working. Imaging, at least with toy examples, where there are a lot of simplifications, but at least this seems to be working. Yeah, and I'm excited to see what else we can do with this data. Thank you.